Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good day to all of you. So for part number 8, we will discuss about a heat exchanger. So in this part, try to differentiate between the heat exchanger and also the mixing chamber that we discussed in previous part, in part number 7. For the heat exchanger will have two moving fluid stream exchange heat without mixing. For example, as shown in the figure, so we have a cross flow heat exchanger. So if we look at the figure, so we have two type of fluid stream. First, we have the fluid stream in terms of steam, where the steam is considered as the hotter fluid that enter the heat exchanger. So the steam will enter the heat exchanger and then come out after the heat transfer process will come out from the from the heat exchanger. And the second fluid stream for this case is the condensate water enter the heat exchanger and come out as a hot water. So the increase of temperature of the condensate water due to the heat transfer process inside the heat exchanger. So the fluid stream in terms of steam, the steam is considered as the hotter fluid, and the condensate water is considered as colder fluid. So due to the difference of the temperature, the steam will transfer heat to the condensate water, so that the temperature of the condensate water will increase after come out from the heat exchanger. Okay, now in terms of simple schematic diagram, so this is the simple schematic diagram for the heat exchanger, where we have two different components. First, we have some sort like a chamber for the fluid B and also the piping for the fluid A. So for this case, fluid A and also fluid B will not mixing during the heat transfer process due to the different component for each fluid. So the fluid A and also fluid B separated with different component. So if we describe the process in the cross flow heat exchanger by using this schematic diagram, in the piping, so we will have condensate water enter the heat exchanger and come out from the heat exchanger as the hot water due to the heat exchange in the heat exchanger. And also we will have high temperature steam enter the heat exchanger. We separate part of the heat exchanger and come out with low temperature steam due to the energy already transferred to the condensate water in the heat exchanger. So this is how we draw this diagram for the heat exchanger. Okay, so now we discuss about the characteristic of the heat exchanger for the steady flow process. So this is the simple schematic diagram to describe the heat exchanger. Okay, we already discussed in previous slide. So in terms of characteristics for the energy transfer for the heat exchanger, so in terms of rate of heat transfer Q dot value, it depends on the control volume selected. For example, so if we select what I call the control volume boundary based on the inner surface of the main body of the heat exchanger as shown in the schematic diagram. So the value of Q dot will be equal to 0 because no energy transfer through the boundary. So we cannot include the value of heat transfer in our energy balance equation. So Q dot will be equal to 0 because the energy transfer process occur within the boundary. However, if we select a different control volume boundary, so for this case, let's say we select what we call our boundary is based on the inner surface of the piping for the fluid A. So for this case, we will have energy transfer. So this energy will cross the boundary that we select. Okay, so for this case, we cannot ignore the value of Q dot. So Q dot will not equal to 0. And rate of work, W dot, because no rotating shaft, no mechanical movement, no boundary work and so on, so no work done for the heat exchanger. So W dot will be equal to 0. For potential energy and also the kinetic energy change, we can neglect both, where delta PE will be equal to 0 and also delta KE also equal to 0. Okay, so we implement this characteristic of heat exchanger to the energy balance equation for the steady flow process. So this is the what I call the full general energy balance equation for the open system with steady flow process. So for this heat exchanger case, so the no W in dot, no W out dot due to no work done during the process. So we don't have any kinetic energy terms involved and also any potential energy terms involved. So the remaining terms only the heat transfer terms and also the E mass in term based on the enthalpy. So the final general equation for the heat exchanger will be Q in dot plus total in M dot multiplied by H equal to Q out dot plus total out M dot multiplied by H. Example 4.11. Refrigerant 134A is to be cooled by water in a condenser. The refrigerant enter the condenser with a mass flow rate of 6 kg per minute at 1 megapascal and 70 degrees Celsius and leave at 35 degrees Celsius. The cooling water enter at 300 kilopascal and 15 degrees Celsius and leave at 25 degrees Celsius. Neglecting any pressure drop, determine A, the mass flow rate of cooling water required, and B, the heat transfer rate from the refrigerant to the water. Okay, so if you look at the example, so the substance that we consider is the refrigerant 134A. So any table that related to this question, so we need to refer to the table for the R134A table. And the condenser is considered as a heat exchanger. Okay, so now draw the simple schematic diagram for the heat exchanger as shown in the slide. So we have water enter the main body of the heat exchanger. In terms of data that given in the question, so P1 equal to 300 kilopascal, T1 equal to 15 degrees Celsius, and T2, the temperature of the water is 25 degrees Celsius. For the refrigerant, M3 dot equal to 6 kg per minute in terms of mass flow rate of the refrigerant. T3 equal to 70 degrees Celsius and the pressure is 1 megapascal. And the outlet of the temperature at the outlet for the R134A is T4 equal to 35 degrees Celsius. Okay, so now we select this boundary based on the what we call inner surface of the main body of the heat exchanger. Okay, so in terms of heat transfer direction, so the heat will transfer from the refrigerant to the water. Okay, because the statement in the question mentioned that the refrigerant 134A is to be cooled by water in a condenser. So the refrigerant must release some heat in order to reduce the temperature. Okay, based on the mass balance equation, so total M in dot minus total M out dot equal to dmCV divided by dt. So due to the steady flow process, so no term dmCV over dt will involve in the equation of mass balance equation. So we'll have M in dot equal to M out dot. So because we have two separate fluid in two different components, so we need to implement the mass balance equation separately for each different fluid that involved in the system. So now M1 dot will be equal to M2 dot equal to mass flow rate of the water MW dot. However, for the refrigerant R134A, M3 dot equal to M4 dot equal to M dot R for the refrigerant. In terms of energy balance equation, so this is the total energy balance equation. So we need to cancel out all the term that not involved based on the characteristic of the heat exchanger that we have learned and also the information that given in the example. So no Q in, no Q out, because these terms actually based on the control volume boundary that we select. So for this case, we select the whole system based on the inner surface of the main body of the heat exchanger. So no Q in, no Q out dot, no W in, no W out dot. So we can neglect the kinetic energy terms and also the potential energy terms. So the remaining terms are only the term for E mass in that involve is enthalpy. So total in M dot H equal to total out M dot H. Okay, so if you implement what I call the specific data for this heat exchanger to the energy balance equation, so we will get M1 dot multiplied by H1 plus M3 dot multiplied by H3 equal to M2 dot multiplied by H2 plus M4 dot multiplied by H4. Okay, so substitute mass flow rate for specific fluid to get more clearer pictures in terms of equation. So MW dot multiplied by H1 plus MR dot multiplied by H3 equal to MW dot multiplied by H2 plus MR dot multiplied by H4. Okay, now we have the final equation for this case, for this problem, for this heat exchanger or the condenser. So because the question asks you to determine the mass flow rate of the water, so rearrange the equation so that we will have the specific equation for the mass flow rate of the water. So M dot water W equal to MR dot multiplied by H4 minus H3 divided by H1 minus H2. So in order to get this one, we need to determine the value of H1, H2, H3 and also H4. MR dot in terms of value already given 6 kg per minute. After this, we need to determine the value of enthalpy for each state that involved. Okay, for the water at the inlet, so first we need to check the phase by using the saturated water table. So T1 equal to 15 degrees Celsius and P1 equal to 300 kilopascal. Okay, so from saturated water table, find out the value of T saturated for comparison. So T saturated at 300 kilopascal is equal to 133.55 degrees Celsius. Compare with the value of T1 given. So T1 lower than T saturated at 300 kilopascal. So the phase will be compressed liquid. Okay, however, the data are not available. So we need to make assumption where we assume that the phase for state number 1 as saturated liquid at constant temperature of 15 degrees Celsius. So again, based on the saturated water table, but now the temperature must be referred to the temperature table. Now we assume as saturated liquid, so we will get the value of H1 equal to HF at 15 degrees Celsius equal to 62.99 kJ per kg. So we can get the value directly from the table. Okay, next, the water outlet in terms of phase, so we need to check again. So we have T2 equal to 25 degrees Celsius, P2 equal to 300 kilopascal. Use saturated water table. So determine the T saturated at 300 kilopascal equal to 133.55 degrees Celsius. Compare with the temperature given for T2, which is 25. So T2 lower than T saturated at 300 kilopascal, and the phase also still a compressed liquid, and the data are not available. So we need to make assumption as saturated liquid. So refer to the saturated water table. Okay, so based on the temperature, because we made assumption, so H2 equal to HF at 25 degrees Celsius equal to 104.89 kJ per kg. Okay, so the value we can obtain directly from the table. Okay, next, so for the water we already complete to determine the value of H1 and also H2. So now we need to determine the value of enthalpy at the inlet and so at the outlet for the refrigerant 134A. Okay, so we use the same approaches, but now we need to refer the table specific for R134A. So the value of temperature is 70 degrees Celsius and the pressure is 1 megapascal. Refer to the saturated R134A table. Okay, check the value of T saturated at 1 megapascal. So T saturated at 1 megapascal equal to 39.39 degrees Celsius. Compare with the temperature given T3. So T3 is greater than T saturated at 1 megapascal, which means the phase for state number 3 is superheated. Okay, so now refer to the superheated R134A table. Okay, find the table for the pressure of 1 megapascal and find the temperature of 70 degrees Celsius. So we can obtain directly the value of H3, where H3 equal to 302.34 kilojoule per kg when the temperature is 70 degrees Celsius. Okay, now the last value of enthalpy is H4. So check the phase for state number 4, T4 equal to 35 degrees Celsius, P4 equal to 1 megapascal. Refer to the same table. So we get T saturated at 1 megapascal equal to 39.39 degrees Celsius. Compare with the temperature given. So the temperature lower than T saturated, T4 lower than T saturated at 1 megapascal. So the phase compressed liquid, data are not available. So make assumption as saturated liquid. So we need to refer to the saturated R134 table. T4 equal to 35 degrees Celsius. P4 equal to 1 megapascal. As saturated liquid R134A. So H4 equal to HF at 35 degrees Celsius. So we need to make interpolation. So the value will be equal to 98.78 kilojoule per kg. Okay, now we already have all the data. So substitute all the data in the equation. MW dot equal to 29.15 kilogram per minute. Okay, so that's how we can determine the value of mass flow rate for the water. Okay, for question B, we need to determine the what I call the heat transfer rate that occur in the heat exchanger. So for this question, so we need to determine different boundary, control volume boundary, where we consider what I call the control volume boundary based on the piping for the R134A as shown in the schematic diagram. So if we analyze again the energy balance equation that involved based on this specific control volume boundary, we can cancel out Q out dot, W in dot, and also W out dot, the kinetic energy in terms, and also the potential energy terms. So the remaining terms from the energy balance equation only Q in dot plus total in M dot H equal to total out M dot multiplied by H. So this is the general equation. So if we implement the data given for the specific case in this problem, so we'll have Q in dot plus M1 dot multiplied by H1 equal to M2 dot multiplied by H2. So refer to the data given. So Q in dot for water plus MW dot multiplied by H1 equal to MW dot multiplied by H2. Okay, so so rearrange the equation. So we got Q in dot W for the water equal to MW dot multiplied by H2 minus H1. So Q in W dot, if you substitute all the value that we have for MW dot, H2 minus and also H1, so we'll get Q in dot heat transfer in to the water is equal to 1218 kilojoule per minute. So this solve all the equation involved with this example.